everyone, this is Yazan. In this presentation, I will talk briefly about the motion system under study and the investigated point-to-point behavior, followed by the proposed frequency-aware basis functions and their use. After that, the use of random walk and sample positioning error in the statistical modeling of the motion system will be highlighted. Obtained experimental results will be discussed, followed by some concluding remarks. A motion system that can move in one direction can be modeled as a cascaded network of mass spring dampers as shown in the figure to the left, along with its associated mathematical model. The motion along extra directions can also be captured in a similar way as shown in the figure to the right. In general, the positioning performance of a motion system varies according to the target position in the working space due to the system structure and interaction with available working pieces. To better understand this behavior, design experiments are usually used to obtain frequency response functions in which the collected data is analyzed and used to experimentally model the system and also to design a suitable linear parameter varying and gain scheduling controllers in an attempt to accommodate the position-dependent behavior of the motion system. To that end, multi-sign excitation signals can be used as control input disturbances, while the motion system position is regulated about a predetermined position throughout an experimental test. This can be repeated with only few representative points of the working space. In our work, we enable characterizing the whole working space using the herein proposed technique, where mainly testing point-to-point position-dependent behavior using statistical means is made possible. Interestingly, adapting input-output perspective such that the control loop is intact allows extending this technique to generic motion systems. As a means of exciting the motion system, we propose an extended version of the sign profile to formulate basis functions that are frequency aware. Despite being applicable at any desired kinematic quantity in this study, we focus on the signal definition at the jerk level. Consequently, the desired position signal can be obtained via mere integration. Working at the coefficients level yield a time-varying switch coefficient set of polynomials that are given mathematically as shown here. The corresponding normalized kinematic quantities are captured in the figure to the left. Recalling the standard definition of the B-Splines, the proposed frequency-aware basis functions are utilized to produce frequency-aware version of the non-B-Spline. The needed evaluation algorithm is provided here to the right, where an example of the attainable profiles is shown in the figure to the lower left. Willing to characterize the shown motion system, simple random walk motion that covers the whole working space is used to enrich the excitation profiles and also to enhance the statistical inference outcomes. Using multi-way analysis of various statistical methods, it's required to write the point-to-point average tracking error as a position frequency-dependent quantity as given in the mathematical model provided over here. To do that, sufficient samples of the tracking error were obtained and processed according to the averaging process given over here. The figure to the right actually shows a portion of the data set obtained during that sampling process. Plotting the recorded tracking errors results in the workspace visualization as shown here at different operating frequencies. To the right, the associated velocity and acceleration profiles of the random walk steps involved are shown with suitable kinematic constraints being imposed. Interestingly, these contour plots can help the operator choosing the right placement of the workpiece such that desirable error levels at any given operating frequency are maintained. Overall, the tracking error of the entire working space is normally distributed. Consequently, MANOVA is used to deduce the desired statistical model of the tracking error. Based on Table 2, the significant coefficients are actually used to come up with a statistical model that approximates the position-dependent behavior of the motion system under study according to the collected data. In conclusion, the position-dependent behavior of the motion system was statistically investigated in this study, where a frequency-aware version of the standard B-Splines was presented. The proposed method can also be applied to characterize other motion systems like CNC milling machines, for example, where the random walk step size can be varied according to the allocated experimental time. The resulting model can be used to detect any faults at runtime by incorporating it into available run charts, as will be investigated in future work. Thank you.